with our ARIMA models, we've been assuming that x of t is stationary. But in reality, what often happens is that xt is non-stationary in the mean. So what can we do in those kinds of situations? Well, this is where differencing comes in to remove this non-stationarity in the mean. And that's the purpose of this particular subsection of the notes. Now, this differencing is closely related to the I of ARIMA, the integrated part of ARIMA, as you will soon see. So here's our full autoregressive integrated moving average model. We denote it symbolically as ARIMA, where we put P, the AR part of the model, Q, the MA part of the model, and D is the number of, or the order of the differencing. Here's then what our full model looks like. I have my AR operator. I have the level of differencing in there, all that times x of t. Then I have the MA operator times WT. WT is assumed to be independent with mean 0, variance sigma squared W. Eventually, once we start estimating these parameters in our model, we will also assume normality. So let's take a look at this new part of the model, the 1 minus b raised to the d power, the differencing part. When we take that times x of t, we could call that all, let's say, y sub t. Then our model then just simply becomes an ARIMA model with p and q as the order of the AR and MA parts of it. So essentially all the stuff that we've been doing for ARIMA models carries over to here now. If we think of, let's say, the 1 minus b raised to the d power times x of t, that part replaced by simply y sub t. Now, why do we use this word integrated? Why don't we call it autoregressive differencing moving average models? Well, the integrated part the name comes from transforming back from the, let's say, the y sub t here, back to the xt through integrating, or in other words, putting together or summing the y sub t's. So the word integrated has nothing to do with calculus and doing an integral. Rather, its meaning comes from putting things together. So for example, if we have first differences then, if I were to take the sum of all my y sub k's, so again d would be equal to 1 here. If I were to take the sum of all my y sub k's up to some point time t, how could I then put this in terms of the x sub t's? Well, I put in what y sub k would be, x sub k minus x sub k minus 1. And then what you'll notice, if you go through this entire sum, we have, let's say, x1 minus x0 plus x2 minus x1 plus x3 minus x2 all the way down to xt minus xt minus 1. What ends up happening is that things start to cancel out. And eventually you're just left with x of t minus x of 0. Of course, we don't have x of 0, so why don't we just call that 0? And there you go. That's how we get from the y's back to our original, let's say, numerical scale that we were dealing with, the x of t's. Now, if you have a higher order of differencing, the same process holds, because remember, second differences corresponds to taking first differences of first differences. Okay, so let's take a look at an example here. Let's look at an ARIMA 111 model. We're going to have phi1 equal 0.7, theta 1.5. I have a variance of 9, and I'm going to have a sample size of 200. What does our model look like if I were to write it out with only x of t on the left side of the model? I'm not going to put in the numerical values for phi1 and theta 1 here. You can see that on your own. So here's what our model looks like for an ARIMA 111. And I can work with the first differences. So I take 1 minus b times x of t. Of course, I get x of t minus x of t minus 1. I just want to have x of t on my left-hand side of my equation. I can keep on then distributing through now the AR part of our model, then move all the AR components, except for, let's say, x of t itself, all over to the right side of the equation, and eventually this is what I get. Work through the algebra on your own. And so this is what our model looks like. So this says, how is x of t coming about? And if I wanted to simulate data from this model, well, I could use a for loop similar to what we've done before to get our x of t. Instead, I can use the ARIMA.sim function to do it for me. So the way I can do this, I say x gets the results from ARIMA.sim. I have my model argument as we've seen before. In my list for this model argument, I have my AR parameter, I have my MA parameter, and now I've introduced a new argument called order, which specifies the PDQ of the model. Now, the P here is 1 because I have a 1 parameter over here. The Q is 1 because I have 1 parameter here. The D then corresponds to the order of differencing. N equal 200, R norm for ran.gen, and my standard deviation is 3 because my variance is 9. Okay, so I've already actually simulated data from this corresponding model. I've saved it into a file called arima111.csv. And so if I read this into an object and take a look at the beginning of it and the end of it, I can compare it to my actual comma delimited file, and indeed I've read it in correctly. I'm going to pull out x from ARIMA111, and that's what I'm going to work with. Okay, so let's go ahead and do some plots here. First of all, here's a plot of my data. And we can see that we definitely have signs of non-stationarity with respect to the mean. So with my observed series, I would expect the mean for the first 50 time points to be greater than the mean for the last 50 time points, just from looking at this from this plot. Let's do some more plots. We're going to do the ACF and the PACF. I'm going to actually draw 6 in one plotting window. So I can use the par function here, which allows me to make a frame by column of 2 rows and 3 columns. So since I'm doing it by column, it's going to put all the plots in by column. So in the first column then, I'm going to have an ACF and a PACF of my observed data itself. And this is what we get. Let me make this a little bit bigger. So we can see from this plot, again, we're just going to look at the first column. Here's my estimated ACF. Notice I have very, very large autocorrelations. This corresponds to what we've seen in past notes. When one has non-stationarity in the mean, you have large autocorrelations that take a long, long time to go down. So even at lag 20, look at how large my last autocorrelation is. And also, just as a reminder, never look at that first line there. That's at lag 0. Now, my PACF plot, one typically would not look at this when I know I have non-stationarity in the mean, but I went ahead and drew it there. Okay, let me come back up. So next, let's do now an ACF of the first differences. So I use the diff function to allow me to do that. Lag equal 1 corresponds to the xt minus 1 here. And differences, I'm only working with first differences themselves. So I'm going to do my ACF and my PACF plot of the first differences. And remember what I said previously as well, that basically, let me actually make this a little bit smaller. Hold on. Remember what I said previously, that basically an ARIMA model, if you have an ARIMA model, let's say for first differences, and you take, you transform your xt to being first differences, so you just have y sub t itself, now you just have an ARIMA model left over. And so what we see here now are the characteristics in this second column here of an ARIMA model. Note that for the first partial autocorrelation, we have a relatively large value. We would expect that because we have one AR parameter. Then, one way to interpret then the remaining part of the partial autocorrelation function is that everything is starting to tail off to 0. Now, when interpreting one of these plots, one can find this to be difficult because knowing when that tailing off starts is not always easy to decide. Maybe you might say, okay, what I see there corresponds to another large partial autocorrelation, so maybe I need 2 AR parameters to my model. Now, for the autocorrelation function, again, don't look at that lag 0 value. What we see here is what we would expect is to have one large, in terms of away from 0, value because we have one moving average parameter, and then the rest of the autocorrelations are tailing off to 0. That could be one interpretation of this plot. Similar to what I just described with the partial autocorrelation function, sometimes it's difficult to figure out when that tailing off to 0 occurs, because you might say, okay, well, maybe I need 2 moving average parameters. I'm going to say it starts tailing off after lag 2. Okay, so that's what these plots look like. And then we could actually compare it to what the true ACF and PACF would be in this particular situation, since I know what AR and MA is. And we can see, and this is what's in the third column, we can see a general agreement between the true and the estimated ACF and PACF. That's why looking at the ACF and PACF is very helpful, then at least to come up with candidate models to examine further. I could do a plot of my first differences as well, and this is what I get. Notice it looks like we have stationarity in the mean from this plot. Okay, so we have some notes here. I've talked about most of them. Let me just take a quick look here. One last note then is that we're going to get to actually estimating models shortly based upon observed time series data. And just to give you an idea quickly of how that can be done, we can use the ARIMA function. I put in my data, I put in my order of my model. Here's P, here's D, here's Q, and this is what we get. The first row of the coefficients table corresponds to phi hat 1. Remember that phi 1 was 0.7, and we get something that's really close to it. Also, here we have our theta hat 1. Remember, theta 1 is actually equal to 0.5 for this model. I'm sorry, 0.4, and still we're relatively close as well. Take into account that standard deviation there, which would be the estimated variance of the square root of the estimated variance of theta hat, and so having a value of 0.4681 would be reasonable to have occur. And so, with a sample size of 20, we're getting essentially what we would expect in terms of what the data gave us corresponding to what we know what the true model is. Okay, so this is the end of this particular subsection, which basically talks about how we get the I in ARIMA.